Hi, I'm Jeff Hollers, and today I'm going to explain how you can use relatively simple sensors and a relatively simple setup in order to measure the magnetic susceptibility of materials. So to start with, you might ask, what exactly is the magnetic susceptibility? Well, it's a measure of magnetization, where magnetization is how a material responds to an external magnetic field. So like in this example, there's a magnetic field pointing to the right, and a diamagnetic material will resist that. It'll form essentially a magnet within itself that points to the left. And a paramagnetic or a ferromagnetic material will instead align itself with that field and amplify it. So your next question might be, how do we quantify this, or how do we put this into math? So to do that, we have to introduce the H field, where H is defined as B, or the vacuum permittivity, minus M, where M is the magnetization. And then this M, if you integrate it over a loop, it equals the bound current, which is analogous to bound charges in electrostatics. And then also B equals mu, where mu is the relative permeability times H. And essentially, if we kind of massage this algebra, we can get M equals chi V over mu naught B, where chi V is this magnetic susceptibility. So then it kind of describes how susceptible a material is to magnetization, how much, if you input a B, what the M that comes out is. So we have this material that's made of tiny little magnets. And then essentially we can view these as dipoles, and if the field that we expose it to has a gradient, it'll feel a force. And then we can integrate and get the total force. And then if we think of there's only gravity and this magnetic force, if we measure a change in mass, that is essentially a way that we can calculate chi V, the volume susceptibility. The first step then is to be able to measure the field. So to do that, we have two sensors here, the SS495A and the HE144X. So the HE144X is what we'll be using for the actual measurements, but we can calibrate it using the other sensor. In order to calibrate it, we use these solenoids, which came from an old transformer in a lamp ballast. And these solenoids are useful because they're very controllable. We can just apply a current and get a field out, and we can take many measurements at different currents to get different fields. After calibration, we can make a spatial map of the field of the neodymium magnet that we'll be using for actual measurements. So this right now is the SS495A, which is close to its maximum field, being measured using an Arduino. It's very, very easy to code and wire. And then also, this is the HE144X, which outputs a difference in voltage, which we use a DMM to measure. Here are the results of those measurements, where you can see at 20 millimeters away, it's pretty smooth, pretty low field. But then at 14 millimeters, it becomes much steeper. There's a lot more gradient. You can see some spatial distribution of it. And then at 8 millimeters, you can see it becomes very, very high field and very, very large gradients at the edge, where it drops off very quickly. And this will become an issue later with it being very sensitive to the position of the sample. Then you can take those mappings and you can calculate a gradient of the field. I did this using the maximums because of that large drop-off became an issue with calculations. And then also you have to approximate the volume. And with that large drop-off, I only used a volume that I knew that the field would be a high value still. So the numbers here represent almost a upper limit on magnitude of chi V because they underestimate the volume. One thing of note is that while most of the materials act like you'd expect they would, from the literature values, the silver coins actually had the opposite. They were paramagnetic when they should have been diamagnetic. This is probably due to them being an alloy and having a different crystal structure than they might otherwise. But overall, essentially the experiment was limited by magnet strength and overall signal strength of simply having a large error from this approximation of the field gradient. So going forward, the easiest way to improve this experiment would be to just simply get a larger magnet so that you have a more even field and a stronger field. This would allow for a lot more measurements of different materials that have smaller signal strengths.